the test, for example. Okay, which one is which one? Okay, now for example, right now we want to calculate sigma 1, and what we did is this. We simply take the free body diagram. The free body diagram is to take the one piece of the cylinder in this cut. So in a way, we'll be able to allow us to expose the influence of the sigma 1. So for example, here we take this cut, then we expose the surface of the wall is the top and the bottom. Okay, here we expose that is the surface of the wall. So, and for each strip of the surface, the area equal to delta x multiplied with t is the thickness. So that is the total area that the sigma 1 can be applied. The same thing down to here. So by taking the equilibrium equations, the stress being corresponding, the stress being induced is to correspond to the pressure that inside here. So here we can see the stress working on the two strips of the area that give us the total force. Internal force is this term. This internal force is to correspond to the application of the pressure. The pressure, we assume the pressure is called the gauge pressure. The gauge pressure basically is the difference between compared to the ambient pressure. Okay, so basically is we call P is called the gauge pressure. This pressure applied to this cross-sectional area, which one? The brown one. The brown one basically is this rectangle. Okay, this one. So this brown rectangles has the width equal to delta x, has the length equal to 2r. The r is the internal radius. Okay, so basically we put into this equilibrium equation nothing more. Okay, so for example here the pressure vessel is only sit there under no other external loading. So here we only have two stresses. One is internal, the hoop stress, and then the pressure. So under this simple equilibrium the equation, then we can find the PR over T is sigma 1. Repeating the same reasoning, we take the free body diagram to expose the influence of sigma 2. So here we take this free body diagram. So we only take the segment of the cylinder. So in the hoop directions, you can see that is the direction on which the sigma 2 will be applied. So sigma 2 multiplied with the those hoop area. Okay, so that is sigma 2 multiplied with 2 pi RT. And here should be minus, and that will be equal to the application of the pressure that applied into the circular brown area. So from here we can find out sigma 2 equal to PR over 2T. Sorry, I think this is a transformation of to the PDF. So here you can see the sigma 1 equal to 2 sigma 2. Okay, that's it. So here for cylindrical pressure vessel, we have sigma 1 equal to PR over T, sigma 2 equal to PR over 2T. That's the equation we can right away to apply to the calculation. And for example, here we might use more circle, say, how about this? I just pick up, yes?
Is that supposed to be at the very, very bottom, the sigma 1
equal? Yes, equal. So why not here we take up this stress element. Okay, for that stress element, we can apply the more circle to see what happens. For this stress element, this is sigma 2, and that is PR over 2T. And here is sigma 1 equal to PR over T. So you can see for this stress element that has been in his principal direction. Those are the principal stresses. Because by definition, as long as there's a no swing stress, then in that specific direction or orientation we define as a principal direction. So for this case here, for example here, if you wish, we can put the artificially define the XY, the coordinate system. Okay, whatever coordinate system you wish to define, you can define here. So for this case, you can see if we want to use more circle, then the average will be sigma 1 plus sigma 2 divided by 2. So that will be PR over T 1 plus 1/2 divided by 2, so that would be PR over T, 3 over 4 PR over T. The radius will be equal to, for this case, is sigma 1 minus sigma 2 squared plus tau xy squared. So the radius is PR over T 1/4. Okay. So with this one, we can draw the circles. So from here to here is 3 over 4 PR over T. And the radius is 1/4. So here we can see the maximum. This is PR over T. So here is PR over 2T. Okay, so one is maximum, one is minimum. So in terms of the design, we have to confine the maximum stress. For example, if we are given the maximum allowable, if we are given the allowable normal stress, then we have to make sure the PR over T is less than the allowable stress. Okay, and on the other side, in terms of this small circle, and what is the maximum shear stress in tank? What is that? The radius, right? So that will be equal to this one. Okay. And we might have one example. I think this one is very similar to your homework. Would that be the same? Very similar. So we'll look at this one. And you can see most of the pressure tank, the pressure vessel or pressure tank is made of the sheet metal. They cut the sheet metal and rope it in a certain way and weld it. Okay. So from here, very likely, you can see if you go to brake mine, if you're going to choose the propane tank, you better to watch the outside any corrosion or not. If that would have something, then you didn't buy it. Okay. Most of the time, the corrosion will be starting from the welding, the defect, or the connection site. So likely for this example, we want to know is you can see this kind of design problems, and said we given the dimension here, we given the welding orientations. So beta equal to 30 degrees, and then we know the allowable stress normal to the welding is 10.5 KSI. And what does that mean? So we can apply the question here. So let me turn up the So with problem statement, then you can see this is a pressure vessel. So from here, if say, let me pick a stress element. So for example, here, let me pick the element is, say, this side. Okay, and then this welding is like this. So the angle here is 30 degrees. Okay, so that is the element here. So here is a thinking process. So this is a stress element I picked there. And in terms of our formula, here is hook stress, right? So hook stress. And here is our longitudinal stress. And if your memory is good enough, then you should know this is PR over T, hopefully. Let me go to the previous page. 1, 2. Okay, you can see for this one, the longitudinal is sigma 2. Longitudinal sigma 2 is PR over 2T. So keep that in mind. The longitudinal is sigma over 2T. So here, this one is PR over 2T. Okay? So right now we have this one, then we made a Moore circle. Let me copy the Moore circle. So the Moore circle is here. So for the Moore circle, we have a sigma and it's a tau. So this point is PR over T, and this point is PR over 2T. So first one, we have to quantify the calculations. So we pick out the information. For example, here, the diameter, the outer diameter is how much? Is 20 inch, and then the thickness is 0.25 inch. So in our formula, R is the inner radius. Okay, so that is the formula, and keep that in mind. And many times people would make mistake is you pick R as the outer radius. No, the R is the inner radius. Let me go to the previous page. Look at this one. In this formula, R, you can see the R is the inner radius. Okay, and use this one carefully. So we back up here. So we can do the thing.
Radius 10?
Oh yes, 10. Thank you. So this one will be equal to how much? The 10 minus T. So will be equal to 9.75 inch. I don't have my numbers with me, so probably I would need some people's help. So therefore, the group will be equal to PR over T. The P is how much? So here we want to determine the pressure, the gauge pressure. So P is unknown, and times R. R is 9.75, and T equal to this one, and the longitudinal will be equal to P times 9.75, 2T, 2 times 0.25. Okay, so here we have those things ready. And now, in this case, you can see right now the welding is in this orientation. This is 30 degrees. The problem statement saying the normal stress to the welding surface has a constraint. You read the certain lines. The allowable stress normal to the welding. Normal to the welding, that means that allowable stress is constrained to the normal stress. Okay, so that means here, in this orientation, 30 degrees, we're looking for is this. Okay, and which is the welding surface. This is the welding surface, right? So that means this represent is aligned to the welding surface. The normal stress to the welding is allowable. So here, this is our key. Will give us this allowable is equal to 10.5 KSI. So that is the interpretation of the problem statement. You have to know which orientations you're looking for. So right now we're looking for this one. Okay? So now we're going to translate that information to the Moore circle here. So right now we can rotate by 30 degrees. So for example, here will be appropriate at this moment. We simply give us the, say for example, this is x-axis, this is y-axis. So once we rotate, this is x prime, this is y prime. So from here you can see our given one, the allowable is in the y direction, is in the y prime direction. Okay, keep that in mind. So this is our x point, this is our y point per the definition of the coordinate systems we use here. Okay. So right now I introduce artificially defined coordinate system so that accordingly label is like this. And now we want to achieve to this orientation. So that means we rotate counterclockwise 30 degrees. So that means we rotate here on the Moore circle by 60 degrees. So 60 degrees. The 60 degrees is double of the 30 degrees we designate here. And why in that orientation, why we rotate in this? Because here we identify that is the 30 degrees, that is aligned to the welding surface. So this would be x prime, this will be y prime. And as long as we can figure out what is this, this will be the coordinate that represent is the normal stress in the y plane. So this one we can see. So this amount must be less than or equal to allowable, right? So as long as we can figure out what is this quantity, then we pretty much we can solve for the problem. So yes.
I'm a bit confused as to how the x and y's were assigned their initial position on the Moore circle and how that, I guess, is related to the sigma allow.
Yes. So again, the thinking process is this. From first I pick the element like this. Okay, so that element we know this is PR over T, this is PR over 2T. And the next step is we want to expose the information aligned to the welding surface, welding orientation. From the problem statement, we know that this is the welding orientation, which is 30 degrees. So therefore, naturally, I want to rotate this element in 30 degrees to align to the welding orientation. And so here I build up the oriented element like this. That's it. And then from this point onward, in order to use the information on the Moore circle, we keep the label. So,
okay,
for example, here,
my question is then why is the sigma, the allowable normal stress associated with the y prime?
Okay, wait a minute here. So here is the transformed x and y prime. Okay. And again, this is the orientation in the welding direction. So the problem statement you can see, the third line,
it's normal.
allowable stress normal to the welding.
Okay.
So that is the normal to the welding. So here we're looking for is this normal component must be less than the allowable. Okay, so that means that represent is by this coordinate.
Okay.
Okay, so now we work on this one carefully. So this is 60 degrees. We utilize this triangle. So therefore, this amount will be, the R will be equal to PR over 40. So therefore, this amount is PR over 40 times cosine 60 degrees. So that would be equal to PR over 80. So therefore, from here to here, that is equal to how much? From here to here, that is equal to, that is our radius. The average is 3 over 4. This is 3 over 4 PR over T. So therefore, from here to here is 5 over 8 PR over T. Are we good? Okay, so this one, that means 5/8 PR over T must be less than or equal to the allowable. So that is our design criteria. So from this case, we will be able to calculate